Okay. Hello, I'm here for a flow simulation around a stationary 2D cylinder. Let's begin. All right, so do a new Fluent workbench right here. Start the geometry. All right, so we're gonna do a 2D cylinder stationary. So we want a large area. So we'll start off by going to sketching, and then we'll create a rectangle, and then we'll go to dimensions and create the dimensions for it. Okay, and for the length, we'll just do 16, and the height we'll do 16 as well. And then for the circle, we will do just a one diameter. But first things first, we need to make the circle concentric. So we'll add two lines, and then we'll go to constraints, go to midpoint, there, and right there. There you go. And now that's concentric. And now we can draw our circle. Start off like that. And then we will trim these lines out. That way we just have the circle. All right. And now go to dimensions and we'll get the diameter of this circle down to 1 meter. That way we have a lot of simulation space to work with. All right, now that that's done, we can do surface from sketch. So we'll select all these lines, these boundaries, and then apply and generate. And there we go. Now we have the surface sketch ready to go, so we can start meshing now. And then open up mesh. All right. Now, first things first, we can just do pre-mesh. That way we can see what's going on here. And now we need to have a lot of cells around the edge of the cylinder. So to do that, we're going to do a couple things. First things first, we're going to we insert a method, put the geometry, sorry, put the geometry to that, and then we'll do triangles. And then now we will do a sizing, and we will select circle edge as a geometry, and we will do 200 divisions right there. That way we get a lot of cells surrounding this the circle. We can do the capture curvature to off, behavior to hard, and that'll be it for the edge sizing. The next step is a inflation. That way the cells inflate from the origin, which is the this little circle right here. So we'll do that, and then for the boundary, select, oops, for the boundary, we'll select that. So now that we have our circle here. All right, and for inflation option, we're going to do first layer thickness. We'll do 60. Um, wait, no, that's not correct. We need to do, yeah, there we go. That's the height of the first layer, not the number of layers. And the maximum layers, we'll do 60. Keep the growth rate at 1.2, and that's good for the inflation. Now we'll go back to the mesh. We set the element size to, let's do 0.8. 8 for the sake of this video. The lower this number goes, the more accurate results will be. And that is pretty much it. Now we can generate. Okay. And now we can see we have a nice mesh with a whole lot of cells around the circle itself. And I go to statistics here. It's around 87,000 cells. Normally you want this to be a little higher, but for the sake of this video, we're just gonna keep it like that. And now we can go on to naming these sections. So we'll go to the edge selection, click on an edge and press N, which is a keyboard shortcut to define the name. We'll define this name as the inlet, define this as the outlet, define the top as top, and bottom as bottom. You could also just select both of these and just call them wall. That would also work too. And then finally the cylinder, we'll just call that cylinder. That way we have all of our sections named. All right, that's pretty much it for the meshing. So now we can move on to the setup. And before we do that, we're going to update. Okay, and now we can start setting it up. Do double precision. All right, and now we're going to begin. So for this video, we're going to do three cases. We're going to do inviscid case, viscous laminar case, and then viscous turbulent. So we will start with the inviscid case. But before we do that, we need to set up some settings. So first thing, we're going to go to the methods. Make sure the scheme is set to simple. Then pressure will set to presto. And then go up here, go to general, and then we'll do make sure everything's right here steady. I mean, these are just default, so these are what we want basically. And right under model, this is where we set the viscous laminar turbulent. So for the first one, we're going to do inviscid, and we're going to set the inlet velocity to 5. Let's do 5 meters per second. All right. And that's pretty much it. We're good to go for our first calculation. So we'll initialize that and then run calculation. We'll do 200 iterations. And now we can start. Okay. And now that that's done, now we can start seeing the results. So under results, go to graphics, and there's a couple options we can do here. We're going to do some contours and path lines. So the first thing we'll do is we'll do contours of static pressure. And there we are. And this this makes sense. You want a nearly perfectly symmetrical pressure distribution because it's inviscid. There is the boundary layer is entirely attached to it as it flows around the cylinder. So the stagnation point here, and then The velocity reaches its maximum, aka the pressure reaches its lowest, top bottom. But since the boundary layer is attached all the way around, there's another stagnation point at the back, which correlates perfectly to the theory. So we can add another contour. This time we'll do the velocity just to see the opposite effect. So we'll do that, and there we are. Now just inverted. Stagnation point at the front. So velocity is its lowest, but it reaches double at the top and bottom, as indicated right here, where it's around 10, and the velocity we set as was 5. So it also correlates to the theory. And now we can see the path of the individual particles. We're going to do a path skip of 50, otherwise it will take a ridiculous amount of time to compute. And there we have it. And as you can see, the velocity comes in, hits it, and then starts flowing around and stays attached perfectly, as shown here. And for the other models, we're going to see that the uh, the flow detaches rather quickly or later, depending on the regime, and we'll see some eddies and vortices. But for now, this is exactly what we want for the inviscid case. So now that I've got that, we can swap over to the laminar case. For the laminar case, we are going to set the Reynolds number to less than the critical number, which is 500,000, because this is an external flow. So we'll go here to the inlet, set the velocity to 2. And we don't need to change anything else. The model and the definitions are all fine. Good to go. Just the velocity for now. All right. And now we can initialize this. All right. And that's good to go. Now we can run the calculation once more. All right. And there we are. Now we could see our results for the laminar case. And here this makes sense. There is a huge wake region, just because due to the nature of the low Reynolds number, the flow is not being energized. So when it hits the boundary layer, it slows down, and then around here, it detaches entirely pretty soon, which creates a huge wake right here. And we can see that again in the velocity contour. We can see these right here and here, these blue spots clearly indicate flow detachment. And right on here, there's a slight speed up of the velocity, which indicates a eddy. And now we can do the pressure contour. And here it's the same. Velocity reaches its 0 mark right around the stagnation point, which is where the highest pressure is. And these eddies create uh, zones of low pressure as well. Correlates pretty well to the theory. And uh, and that's pretty much it for the laminar case. And for the final case, we will enter the turbulent regime. So we could just realistically just select any one of these viscous models, but it does need to be in the laminar, or sorry, the turbulent zone, which means Reynolds needs to be higher than 500,000. So for our case, we are going to select the velocity as 8, which will correlate to a Reynolds number of around 550,000, I think. So we'll go ahead and apply that. And now we are good to go for the turbulent case. So we can initialize that. Oop. That's what I want to do. And then run our final calculation. All right, there we go. All right, so now that we entered the uh, turbulent regime, the wake theoretically should be lower or smaller due to the fact that the flow is being energized from the high Reynolds number. So we can go to the velocity contour. And indeed, we see this effect because the boundary layer separates much later than the laminar case. The laminar case, the boundary separated right here. This is a few, yeah, this is much further along the circle the boundary layer separates. And we could also see that the wake is much smaller than the laminar case. The same goes for the pressure. Um, pretty nearly evenly distributed. And then for the path line, we'll show that as the final one. And here we are. And we can see very clearly that the wake is indeed smaller than the laminar case, which again correlates perfectly to the theory and is exactly what we want. And that's about it for this tutorial. Thank you for watching.